Hello, chemists. This is Ms. Placino, and you're watching Lesson 7.1 on Intermolecular Forces. In today's lesson, we're going to look at what types of forces are going to hold molecules of a substance together. You almost never work with a single molecule in chemistry. You have billions of them, moles of them together. And the fact that there are many molecules present is going to kind of change some of the macro properties that we see of them or how they behave as a group. So let's get into some lesson goals. First, we're going to recall how to determine the polarity of the molecule. Intermolecular forces are really closely related to polarity. We'll also be able to describe and identify the three types of intermolecular forces. We'll understand how intermolecular forces impact the boiling point of a substance. And we'll be able to predict what type of intermolecular forces a molecule will exhibit. This is the big one. It's really going to tie in Lewis structures, predicting polarity, and then connecting it to the three types of intermolecular forces we're going to introduce today. So it's going to be a busy lesson today. I hope you're ready to go. When we talk about intermolecular forces, we are looking at attractive forces that exist between molecules, and just forces of attraction between multiple molecules. So if we take a look at these two water molecules, for example, up to this point in time, we've been studying what could be called intramolecular forces, kind of that pair of electrons that are being shared between the hydrogen and the oxygen atom. In this lesson, we're going to shift gears and we're going to look at the attraction between molecules. So within at least two different molecules, these are called intermolecular forces. If you think about like an interstate highway, that's got to connect at least two states. If your guidance counselor tells you you need to work on interpersonal skills, they're talking about your social interaction with others, not with yourself. So there are a variety of different types of intermolecular forces that exist, and it's just describing this attractive force between two molecules. There are no electrons being shared, there's no ionic, no covalent bonding, none of that. It's just attraction between molecules. So let's look at that. Actually, before we get into that, let's kind of review polarity. All right. Intermolecular forces are directly connected to whether a molecule is polar or nonpolar. I know it's been a little while since we've talked about polarity, so let's review. When we talk about polar molecules, kind of a quintessential example is H2O. If we look at water, we have an uneven charge distribution. Oxygen is highly electronegative, meaning it's going to pull the shared electrons in the OH bonds towards itself. That's going to leave the hydrogen side of the molecule to be a little bit positive. So we see that separation of charge. Polar molecules tend to behave like little magnets. Kind of one quick and easy way to assess polarity is to look at symmetry. If you have a fairly asymmetrical molecule, so maybe 1 or 0 planes of symmetry, it tends to be polar. Another good thing to look for, doesn't show up in the notes, but you can probably jot it down. You've got those unshared electron pairs on the central atom. That often leads to a molecule being polar. On the other side, we've got nonpolar molecules. Picture a nonpolar molecule in your head. There's a good chance you're thinking about some tetrahedral form of carbon. Methane, CH4, is a great example of a nonpolar molecule. Here we see a very even charge distribution. We don't have that positive and negative side of the molecule the way we see in water. Nonpolar molecules at this point in the game tend to be highly symmetrical. So 2 or more planes of symmetry. That's definitely the case with something like CH4. And it doesn't show up, but it wouldn't hurt to jot it down. Your nonpolar molecules tend to have no unshared pairs of electrons on the central atom. I hope that served as a quick reminder of how to assess whether a molecule is polar or nonpolar. Let's look at some intermolecular forces. We're going to start with dipole-dipole. And the word dipole is really just a synonym for the word, or the phrase, polar molecule. HCl is an example of a polar molecule. We have a a partial positive charge on our hydrogen and a partial negative charge on our chlorine atoms. You can kind of imagine a bunch of HCl molecules being together and behaving like little magnets. Let me write that down. Think dipole-dipole, think magnets. You know from experience that the positive side of one magnet, or the north pole, will be attracted to the opposite charged pole. We've got the same thing here. A positively charged or partial positive charged hydrogen of one HCl molecule would be attracted to the partially negative charged chlorine atom of a neighboring molecule, and it's going to kind of cause the molecules to stick together. Again, you need a polar molecule in this case. We cannot observe dipole-dipole with nonpolar molecules. All right. Some types of dipole-dipole attractions are so strong they get their own category. We call this type of intermolecular force hydrogen bonding. I'm sure you can use your amazing powers of deductive logic to figure out which element is always present in hydrogen bonding. Yeah, hopefully you're thinking hydrogen. Water is an example of a molecule that exhibits hydrogen bonding. We know we've got the partial negative charge on the oxygen, partial positive charge on the hydrogen. We're just going to see those attractive forces existing between water molecules. But this is a very specific type of dipole-dipole. Hydrogen bonding occurs when hydrogen is bonded to a small, highly electronegative element. So if you think back to the periodic trends and Unit 3, electronegativity, that's the ability of an atom to pull electrons towards itself in a bond. Hopefully you remember that fluorine is our most electronegative, and then kind of as you move further away from fluorine, you're going to see a decrease in electronegativity. So hydrogen bonding takes place when hydrogen is covalently bonded to nitrogen, oxygen, or fluorine. We're going to see a big difference in electronegativities, making this a very polarized bond. So the oxygen is really negative, the hydrogen is really positive, and that's going to cause a strong attraction between water molecules. Our last intermolecular force is for nonpolar molecules, and we call these London dispersion forces. You might hear them just called dispersion forces. Both are perfectly fine. I'm going to explain this diagram in a little bit more detail in just a moment. London dispersion forces are weak attractions between temporary dipoles. All right, if we think about our dipole-dipole as being like magnets, we know that magnets will attract one another. Have you ever had like balloons attracted to one another? You take a balloon and rub it on your hair. And if you do that with a couple balloons, you can charge them and they will stick together temporarily. That's kind of the same idea with what London dispersion forces are. Here we've got two nonpolar molecules, some sort of diatomic, maybe like a chlorine or something. We know that the electrons are kind of zipping all around in our molecule, so it's not difficult to imagine that at one point in time, you end up with more electrons on one of the atoms than the other, giving you a slightly negative and slightly positive kind of like split of the molecule. That in turn could cause that positive charge, more electrons to go over in the neighboring one to give us a slightly negative and slightly positive charge. And we've got this temporary attraction. It's really fleeting. It's not going to last forever because the electrons are constantly moving, so they can move again, and then that charge imbalance can be corrected. And then, you're probably going to see that happening with the neighboring molecule. So just very temporary attractions between two nonpolar molecules. And that's kind of the key with London dispersion forces. This is the only type of intermolecular force our purely nonpolar molecules can exhibit. So earlier I mentioned that intermolecular forces can have an impact on properties. The one property that I really want to look at today is boiling point. So in order for a substance to boil, those intermolecular forces of attraction have to be broken. Think about it. When we talk about boiling, we're talking about the change from liquid to gas. It's still the same substance, but we know from experience and probably from prior science classes that in the liquid, all of the molecules are really close together. They're tightly packed. They've got the freedom to move around, but there's still a high degree of attraction. As we boil a substance, we need it to become a gas. You can kind of actually look over here, again, at this little icon. You get even more space between the molecules. In order to pull that off, you've got to break intermolecular forces, so these attractive forces between molecules. So again, here we've got water. We know that water exhibits hydrogen bonds. And in order to get liquid water to turn into a gas, I've got to break these bonds so that the molecules are kind of free to move away from one another. If you want a substance to boil, based on your own life experience, what do you usually have to do with it? Yeah, you've got to heat it up. If you want water to boil, you're going to stick it in a pot and put it on the stove, turn it on, and as you get more and more heat provided to the molecules, they're going to start moving around faster and faster. You can imagine them moving around so much that these attractive forces between them are going to break. Kind of imagine if you're holding hands with someone and you're just kind of walking at like a leisurely pace. It's really easy to stick together. Now, if suddenly you have to run, you have to break out into a full sprint, it's going to become very difficult to stay connected to that person. So there's a good chance that you're going to have to like let go of them in order to reach top speed. Kind of the same idea here. For a lot of compounds, there is a direct relationship between molar mass and boiling point. In other words, the greater the molar mass, often the higher the boiling point. This does not always hold true, and we're going to look at some examples, but a lot of times that is what we will observe. All right, so in your notes, you have this chart of the group 14 hydrides. So these are compounds that are composed of a group 14 element and hydrogen. We kind of made things seem very black and white when we first started talking about bonding, that like a metal plus a non-metal would always yield an ionic compound. In reality, it's kind of more of a like sliding scale. You've got like degrees of covalent and ionic character. I will tell you that for all four of these, regardless of whether you're bonding with a metal, a metalloid, or a non-metal, you are going to see covalent bonding. So what I'd like you to do is pause this video. I'd like you to draw the Lewis structure for each of these four molecules. I'd like you to predict whether that molecule will be polar or non-polar. That's what the N and the P stand for. I'd like you to predict the intermolecular force that will be present. We've got dipole-dipole, hydrogen bonding, London dispersion. MM stands for molar mass. Now we learned how to calculate that in the previous unit. So go ahead and calculate that out to the nearest whole number, or possibly the tens place, and then we'll review it together. So pause the video, get those set up. All right, so let's start checking your work. I went ahead and I drew all of the Lewis structures. They should look strikingly similar. You've got your central atom changing, and then you've got four hydrogen atoms bonded to it. If we had to go through and predict polarity, well, we can either use symmetry, we can talk about distribution of charge, we can look at number of unshared pairs of electrons on the central atom. Regardless of your approach, I hope you're coming up with non-polar for all of these molecules, right? I put down the molar mass. I trust you can figure that one out on your own. Let's talk about intermolecular forces. Since all of these molecules are non-polar, what is the only type of intermolecular force they can possibly exhibit? Hopefully you're thinking London dispersion forces. So I'm just going to abbreviate those. You are welcome to do the same. LDFs. All right, so let's look at a couple things with these molecules. As you're just looking at the Lewis structure, what sort of geometry are all four of those molecules going to exhibit? I know we're going back to some old material. Hopefully you're thinking tetrahedral. We've got the central atom, four atoms bonded to it, no unshared pairs of electrons. That's why they're all nonpolar. I want to look at the relationship between these two values, molar mass and boiling point. As we take a look at the molar mass, as we go from tin tetrahydride to germanium tetrahydride, so on and so forth, we're seeing a decrease in atomic mass. We're going through and also seeing a decrease in boiling point. It's getting easier and easier to boil them. It's more and more difficult to condense them. I know it's a little bit strange to look at it with the negative signs. So out of this group of four, which of these must have the strongest intermolecular forces? You might be thinking, well, wait, aren't they all LDFs? Yes, they are all London dispersion forces, but based on the boiling point, which molecule has the strongest London dispersion forces? Yeah, it's going to be tin tetrahydride. We see the greatest boiling point, so therefore it must have the strongest intermolecular forces. You can probably conclude, or hopefully conclude, that methane, CH4, is going to have the weakest IMFs. It's got the lowest boiling point, so we have the weakest forces of attraction between methane molecules. Just to kind of summarize, all of these molecules have a tetrahedral shape. We know that they're all nonpolar. Therefore, they're all going to exhibit London dispersion forces. Or again, if you want to just call them dispersion forces, that's fine too. The relationship between molar mass and the strength of intermolecular forces? Well, the greater the molar mass, the stronger the intermolecular force is. We saw that by looking at the boiling point data. When molar mass is higher, your boiling point is also higher. And as molar mass decreases, so does the boiling point. I want you to repeat the same general idea for the group 16 hydrides. Pause the video, draw some Lewis structures, predict polarity, predict IMFs, calculate molar masses, and check in when you are finished. All right, here we've got the group 16 hydrides. Lewis structures, just like with the group 14s, they all should look pretty similar within the group. If you chose to draw these molecules as like straight lines, that's completely okay, although this is probably a better representation at an angle. So I've got the same shape repeatedly. If I've got to go through and assign polarity, we have like one plane of symmetry. We also see unshared pairs of electron on our central atom, so a high likelihood that these are polar molecules, all of them, regardless of what the central atom is. All right, let's talk intermolecular forces. Polar molecules, we know that we can have a dipole-dipole attractive force or hydrogen bonding. Hydrogen's present in all of them, so all of them must be hydrogen bonding, right? No. Hydrogen bonding only applies when hydrogen is bonded to fluorine, oxygen, and nitrogen. So technically, it's only water that exhibits hydrogen bonding. The other three compounds are going to be dipole-dipole forces. All right. Now that we see some different types of intermolecular forces, let's review that relationship between our molar masses and our boiling points. All right, as we go from like towards the bottom of group 16 and make our way up to the top, we see decreases in atomic mass or molar mass. Again, however you'd like to think about it, really not a big deal. Pretty much what you would expect. If we take a look at the boiling point, as molar mass decreases, so does boiling point, just like you would expect. Until here, what the heck is going on with water? You've got these other three molecules as gases at room temperature, where water is going to be a liquid with a very high boiling point. What is happening here? Hopefully you're thinking, well, maybe it has something to do with the intermolecular forces. And that's exactly right. In this case, water must have the strongest intermolecular force, strongest IMFs, because it's got this crazy high boiling point despite a very low molar mass. In this case, H2S, hydrogen disulfide, dihydrogen sulfide, must have the weakest IMFs. It's got the lowest boiling point. Then H2SE, and finally H2TE, before we get to H2O, our strongest. So just to do a little bit of review, all of those molecules have the bent shape or bent geometry, therefore are going to be polar molecules. If we try to rank the group 16 hydrides from strongest to weakest, I already did this, it's H2O, H2TE, H2SE, and H2S. Even though water has the lowest molar mass, it's got the strongest intermolecular force. Well, how do we know that? Because it's got the highest boiling point. If you take a look at CH4 and H2O, they have very similar molar masses. 16 grams per mole for methane, and 18 grams per mole for water. Why are their boiling points so different? Yeah, this all comes down to intermolecular forces. IMFs can have a huge impact on something like boiling point. Strong intermolecular forces are going to hold those molecules together, and it's going to require a lot of energy to get them moving fast enough to break away from one another. Our nonpolar molecules, like CH4, have London dispersion forces. So when their molar masses are about the same, chances are the one with the strongest intermolecular force will have the greatest boiling points. You definitely have some practice problems that have you go through just reminding yourself on how to draw these Lewis structures, identify the polarity, and then match it up to an IMF. I will let you practice with those on your own. So here's just a little bit more info on hydrogen bonding.
Hydrogen bonding occurs when a hydrogen atom is bonded to a small, highly electronegative atom such as nitrogen, oxygen, or fluorine. In this example, its combination of high electronegativity and small radius enables fluorine to draw electron density away from the hydrogen atom. The HF bond is highly polar. Because hydrogen has no core electrons, its nucleus is left practically unshielded. This gives the hydrogen atom a relatively high partial positive charge, which is powerfully attracted to the partial negative charge on the fluorine atom of a neighboring HF molecule. Although hydrogen bonding is a type of dipole-dipole interaction, some hydrogen bonds more closely resemble ion dipole attractions in magnitude. In a series of similar compounds, such as these group 4A hydrides, boiling point typically decreases with decreasing molecular mass. This reflects the smaller London dispersion forces that exist between smaller molecules. Note, however, that in the series of group 6A hydrides, although the same boiling point trend is observed for the heaviest members of the series, the boiling point of water is anomalously high because more energy in the form of heat is required to break the hydrogen bonds and separate the molecules. The difference between the expected boiling point of water and its observed boiling point is due to hydrogen bonding.
So that's just another way to kind of represent the information that we collected. I know some of you like to see it as a graph instead of as the numbers. Hopefully it's really driving home that same point, that we see this crazy high, unexpected boiling point for water based on the fact that it has hydrogen bonding. It makes a huge difference, and that's why liquid water exists at room temperature. If it wasn't for hydrogen bonding, yeah, we'd probably see a boiling point not too dissimilar from methane's, and there would be no liquid water present at room temperature. So really important. Speaking of bonds and things being really important, I just want to quickly make a connection between something you probably learned about last year in bio and what we're talking about with IMFs. Last year, my guess is you learned about that nitrogenous bases that are present in DNA and that the bases always pair up in the same manner. It has to do with intermolecular forces. Why do you think it might be a good thing that the strands of DNA are connected by intermolecular forces, these forces of attraction between molecules, rather than intramolecular forces, something like a covalent bond? What type of IMFs hold the strands of DNA together? So I've got some of your pairing, the CG and AT pairing. Go ahead, brainstorm on that, think about it. It is really interesting, in my opinion, to start making these connections about things that you learned in the past. All right, chemists, I'm sorry that ran a little bit long today. We did have a lot to cover. Thank you for tuning in, and I hope you found this helpful.